Hello, I'm Linda Smith from Indiana University. I am not a roboticist. I am a developmental psychologist who studies the mutual dependencies among perceptual, motor, cognitive, and language development in infants. And today I'm going to talk about principles from human development with examples particularly drawn from the development of object perception and object name learning. The big idea behind developmental robotics is the idea of using the same building processes that biology does. And this is a really good idea because these devices right here are extraordinary learning machines. Babies develop their competencies without knowing exactly what they have to develop. They are highly adaptive. They might learn to become efficient tool users with chopsticks or efficient tool users with forks and knives. The openness of their possibility for learning and their adaptive ability gives a way to think about how to build smarter and more general robots. So here is what this lecture is about. This lecture is about why and what is development. What does it mean to say we're taking a developmental approach? And when I talk about that, I'm going to talk mostly about developmental systems approach, which within robotics is often thought about in terms of the brain-body environment system. Another point that I want to make is that the pathway is itself the topic of study and a clue as to how to build better robots. A third concept is developmental niches, big concept behind what I will tell you. And then I will give case examples from infant learning about objects and categories, case examples that illustrate the importance of multimodal exploration, of the interdependence of pathways, of multiple pathways, and social scaffolding. So to begin, developmental systems theory. The idea, development is a history-dependent, multi-leveled, multi-causal, contingent, and opportunistic process. It is a process that is very much like evolution and like culture, through which local changes, local events in the here and now are dependent upon past history, everything that's come up to this moment, and on the context at this local here and now, and that creates change in the system. And over time, and the aggregation of all those local changes, you can build new structure. So I'm not going to talk on and on about developmental systems theory, but I think it'd be very interesting for folks to look at. And here are three books on this topic that have been influential and I think offer good insights that would be useful to roboticists. So to the first point here, principle one, brain, body, environment. This is kind of the cognitive science or robotics version of developmental systems. This figure here was first developed by Randy Beer, giving the citation there. And what he noticed is that adaptive intelligent systems who are autonomous in the world, you could think of them as made up of a series of couplings, of the brain to the body, but then the body back to the brain, and of the body to the environment, and then the environment back to the body, with mutual dependencies in all directions. When you think about this from a developmental systems point of view, though, you have to think of these couplings as changing over developmental time, and in fact, the whole brain-body environment system changing over developmental time. So the first point I want to make is that the brain-body environment system, that figure that Randy Beer made, is not the same system for a 3-month-old and a 2-year-old. So if we look at these babies in the figure, that little newborn baby up there in the corner with its dad's hand holding against it, the brain-body environment for that baby is fundamentally different for the 3-month-old, for the 7-month-old playing with his feet, for that 14-month-old exploring his first lobster, or for the 2-year-old involved in pretend play. The body-brain environment, all three components change because the baby's body the sensory-motor system changes, and every change creates a new learning environment and new tasks to be discovered. There is a sense in which thinking about building an intelligent system in this way, one where the brain-body environment, the tasks to be learned, are ordered and changed systematically, might be a very useful approach. The way to understand how this brain-body environment changes, or a way that people doing human development often think about it, is thinking about it in terms of pathways, where the pathway itself is the topic of study. A developmental pathway may be defined as the route or chain of events through which a new structure or function forms. Now, interestingly, the pathway is not the same as a mechanism. So if we were to talk about the mechanism through which that baby who's sitting there in the little infant seat playing with an object, if you're going to talk about the mechanism through which that baby held on to objects or grasped them, you would be talking about a certain set of processes, motor, sensory, brain, that enable a child to hold on to an object. But the pathway is what is the developmental history that brought the baby to that point, okay? Whoops. And for object manipulation, trunk control, being able to sit stably, is part of the developmental pathway. It's not the mechanism through which you grab objects, but it is part of the developmental pathway. You have to go through that point to be able to sit there and play with objects. Not falling over is critical to developing an ability to handle and manipulate objects. Okay. When you think about the pathway and how the sensory motor system changes and what the child has to build to move along, then one way of thinking about development is in terms of a series of developmental niches. The environment for the young learner, the regularities in that environment, and the tasks to be solved in that environment change because the body and the activity of the developing infant changes. And in general, and a point that I emphasize in my own research and are emphasizing in today's talk, is that motor development is actually a key gate on infant experience. It's a key component of many pathways that orders the kind of environments that an infant is in. And I want to make this point to you by showing you 3 movies. And these movies are ones in which we take first-person views of babies' worlds by putting head cameras on them or head-mounted eye trackers as they go about their business. And what we're doing is measuring the momentary environment as a function of the moment-to-moment bodily activity of the perceiver. So, the first movie that I'm going to show you here is from a 3-month-old. So the 3-month-old is wearing the head camera, and what does she see? She sees her mom and a toy. 3-month-olds see what people show them or what is in the location where people put them. They don't have much control, okay? They see what mom shows them. Now, here's a very different view. This here is a 7-month-old crawler. And what does that crawler see? Oh, that crawler sees a rug, dirt spots on the floor, a lot of great optical flow, by the way. This is really new and different kind of visual information that probably plays an important role in the development of the visual system, and it comes once a baby starts to crawl. Now, here we have a 12-month-old. And this 12-month-old, is sitting and playing with objects. Now look at this. This is very stable, very calm, offers little opportunity for mom to tell you something as the child is handling that object. And throughout most of today's talk, I'm going to be talking about object manipulation. But what I want you to see from those 3 videos is that babies have ordered environments. Early on, they see certain kinds of things in their world, and they embrace certain kinds of tasks, looking at faces, face-to-face play with mom. Then as they develop and they get more autonomous and can move and do different things, they put themselves in a different set of statistics, a different set of regularities in the world. So development goes through these ordered environments, ordered sense of tasks. It is that are created by the learner's own activities and by the learner's previous history. So these developmental niches, these sets of ordered environments are not like batch statistics, okay? Instead, these young learners are given a guided walk through a search space for solutions and for tasks. And that guided walk is determined by their own activity, which is determined by their own developing sensory motor system. So a roboticist might want to think about how to build a robot that selects an ordered set of environments, that structures the data in time, and think about what that ordering ought to be. Why should newborn infant babies sit in little seats and mostly look at the world, building a lot of visual statistics, before they actually start to reach for objects and manipulate them, before they get up and walk across the room, okay? What is those different set of statistics building? What kind of a system? I want to give you one example of, this is kind of new work from our lab, but that is, I think, interesting in thinking about what ordered statistics might mean. Here we have collected first-person view data from head cameras on babies, infants from 1 month to 24 months of age. Each of the infants wore the head camera at home. We weren't there through their daily activities for about 6 hours. And two things that we coded initially were the presence of faces, a big important stimulus for a lot of social development, both for children and for robots, and hands. We chose hands because hands do instrumental acts, and they act, they're the things that make things happen in your world. And what we found, so if you look at that scatter plot in the, called A, on the y-axis shows how many faces in a proportionate time, and the age of the infants in months. And what you can see, each dot is an individual infant. What you can see is the frequency of faces in infants' visual worlds declines markedly with age. In the little graph on the bottom, the B graph, where it says how many hands, each dot again is an individual child, and it's showing the proportion of hands in each child's visual corpus as a function of age. And you can see that hands, and now these are both the hands of the child and the hands of social partners, increases dramatically. And that third graph, C, that just shows the delta score for the individual infants, faces minus hands. So what do you see? Early in development, up to 6 months or so, baby's world is dominated by faces of people. Later, baby's visual world is dominated by hands. And you should know that all those hands are not just hands lingering, they're hands holding on to objects. 80% of all the hands that we see in these images are in contact with an object. So what does this mean for why face processing is so special in the visual system of humans? What role does having solved the face problem early do for social development, for learning language, for learning other skills in the infant? Because this is going to be the child's history. They solve this problem before they attack another one, okay? So again, the point here is that we see ordered developments in the visual input from faces to instrumental acts, and I think there is an important theoretical question as to what are the computational consequences of this kind of ordering. Now I'm going to turn to a series of case examples, mostly from thinking about objects and object manipulation. And the fourth principle that I think you could take from development into developmental robotics is that infants, through multimodal exploration, discover and solve tasks. Babies don't have one sensory system. They have multiple sensory systems, hands and eyes and the motor components. And they are all continuously coupled in the world, in the moment, through the body, okay? Now, this idea about these sensory motor couplings is the core idea behind Jean Piaget's theory of sensory motor intelligence. What he argued was that babies, by interacting on the world, learn to coordinate different sensory modalities. So an example that from his work was one in which he would take a baby, let's say a 3-month-old, who'd never seen a rattle and never shaken a rattle, and he'd give that baby the rattle, put it in his hand, right? And baby doesn't know anything to do with it, but baby moves, and the rattle makes a noise. So baby can see and feel, and he can hear. I could have had a third box over there that talked about sound. So he moves it, he sees it, he hears it, okay? And after a bit, the baby is no longer randomly doing it. You can see the baby, this is young as 3 months. He'll move it and stop. Nothing happens. He'll move it and stop. He looks like he's hypothesis testing. Am I doing this? Am I making this thing go across my sight? Am I making these sounds happen? And what Piaget said was that babies actually, through this kind of coupling, the coupling of different sensory modalities in real time to the same physical world, discovered tasks and solved tasks, okay? The point I want to make is that having multiple sensory systems is computationally powerful. What they give you is heterogeneous, overlapping, but partially redundant takes on the same reality. And they're takes that are time-locked together in real time, tightly coupled. In a demonstration of the computational importance of this, Rieck and Edelman devised a system that could teach itself to recognize all varieties of letters, not just A's, every letter of the alphabet, and with quite varied fonts and handwriting. And the way they did it was like this, okay? They took, this is really Piaget's core idea, they took 2 different ways that one could recognize letters. One was feature mapping, sort of standard kind of Hubel and Wiesel ideas, right, where you have angles and curves, and you just kind of build up the components. But they time locked that to a tracing one, where you might, go like this, okay? Okay, so the device would trace, and while it was tracing, it would be exciting feature maps. But these 2 systems, okay, time-locked, okay, and connected to each other through just basic Hebbian learning, trained each other up to very abstract ability to recognize A's, okay? So the point is, by having these different takes on the same reality, but that are coupled to the same reality in time and that mutually influence each other, the system can, without a teacher, without right or wrong, without feedback necessarily, discover quite abstract solutions, okay? It's very much what Piaget was saying in The Origins of Sensory Motor Intelligence, except without a computational side, okay? So the other thing that's interesting, I think, in terms of advancing work in developmental psychology, are a number of labs are going after these ideas and are showing that changes in one coupling, so what you might learn about vision through touch, or what you might learn about touch through vision and playing with a rattle, that they can have cascading effects downstream on seemingly other unrelated tasks. And one of the best examples of this is a study by Amy Needham and her colleagues. And what they did is they put Velcro mittens on babies and Velcro on objects. And they did this for very young infants, 3 months old, too young to actually effectively reach and grab an object. But they gave these babies experiences ahead of their time in coordinating eyes and hands and getting objects and moving them about themselves in space. And so you could think about this as teaching eye-hand coordination. But it has cascading consequences in terms of mouth exploration, oral exploration, cascading consequences in terms of means-end tasks, problem solving, and in terms of spatial judgment problem. That babies who participated in the sticky mittens experiments go on to develop faster ahead of time in later emerging abilities. And these effects show cascading effects of the sticky mitten experience months down the line. The little diagram I've drawn up there gives a sort of way to think computationally about how it's happened. Let's say you couple two systems, A and B in one task, eyes and hands and grabbing an object. But then in some other task, you need to couple, you know, eyes and mouth, or eyes and audition. Well, you've already changed the B, the vision one that I'm saying in the middle. So by coupling A and B and solving some task, you've actually tuned up B a little bit for task one. But now when you couple B, let's say vision with audition, the coupling that is happening there depends on the history that's already been, what's happened in the B, okay? And so you can, advances in one task that seem very far away may have cascading effects quite down the line. In collaboration with Lisa Burge and Olaf Sporns, we have a paper that pursues this in terms of changes in brain functionality and brain connectivity, this core idea that you might also find interesting. I also want to bring to your attention that these same ideas are apparent in Pierre-Yves Oudayer's robotics work, in which he basically uses the core ideas that I've just talked about exploration and discovering tasks and solving them in ordered sequences, placing robots and their social partners. He uses dog robots to make those same points. And that's a line of work that's also well worth looking into. Okay. So now to principle 5, which is interdependent pathways. Okay. The ability of this baby at 12 months to sit there and steadily hold and look at that object is extraordinarily important. We know that object manipulation and how well babies do it at this age and how coordinated their hands and eyes are predicts later language learning, plays a big role in visual object development. And we also know that the ability of the baby to manipulate this object and to stably look at it in time is highly dependent on previous achievements in sensory motor development, in head stabilization, and in trunk control. And I want to give you, so there's a whole variety of things. You're going to go from trunk control to learning nouns. And so what I want to do is just give you a few examples from this where early developments, I'm not going to talk about these, but developing trunk control and head stability enables you to actually sit and manipulate objects. And then what I will tell you a few examples about is how doing that has effects on visual object recognition. And I will point you to the literature that shows how that influences object name learning, okay? So when you sit and hold an object, you generate views of that object, okay? Not what people show you, but you, through your own manipulation, are generating different views, okay? In one study that we did, again, another head camera study, and in this study the children were 12 to 30 months of age, we took videos of the views of objects that they were showing themselves, and then we mapped out precisely what those views were. And what we built was what's called a dwell map. This is an adult dwell map if you give adults views of objects to hold. So if you were to think of the object as sitting in a three-dimensional sphere, I could draw little regions in it, okay? And then just like you do with the globe in a map, I could cut it open and lay it flat. And so I would get the heat map that you're seeing there. And without my even telling you anything about how the heat map is showing different regions of the objects, you can see this is a dwell map for adults, that when they hold an object and look at it, they do not sample all the possible views of that object. They are very selective. They sample 4 views, okay? Very tightly organized, their views. I'll tell you more about what those views are in a minute, but what we wanted to know was what babies did, okay? What does a dwell map for manually generated object views look like for 12 to 30-month-olds, okay? This is what it looks like, okay? Now, the little view map up in the corner is a 1-year-old, then we have a 1.5-year-old, a 2-year-old, and a 2.5-year-old. Without even knowing what the axes are on this, you can see a lot about what's happening. The 1-year-old is kind of a schmear. And by the time you get to the 2.5-year-old, it looks beginning to look like the adult. There are definitely some views of objects that when they're holding them and looking at them, they're biased to show themselves, or biased to hold objects, so that these are the views that you see. And you can see with development that you're going from kind of schmeary up to hot spots that are much more like the adults. But if you look back at those 1-year-olds, you can see that there are, maybe we should call them warm spots that are in some of the same regions as those really refined adult hot spots. So what are the views that adults show themselves and that babies are sort of showing themselves? Okay. What they're showing themselves are the planar views of the objects. The planar views are the views in which the axis of elongation is perpendicular or parallel to the line of sight. And adults are biased to show themselves the planar views. And they're also biased to show themselves the planar views in which the major axis, the longest axis, rotates in depth. Okay, so not this way, but that way. All right. And that's what children are showing themselves. Okay, they are showing themselves they're showing themselves the planar views, and they have smears across the top and the bottom because they sometimes hold the object upside down. And the other thing you should note from this is that the smears that connect the 1-year-old's warm spots and that connect the 1.5-year-old's warm spots, those are because they, like adults, are rotating that major axis in depth. Okay. All right. So why is this important? This bias for views around the rotation of the major axis in depth is generating the visual information, the visual statistics on which 3D object recognition will depend. Okay. The bias for the flat sides, the planar views on that rotation, are giving the statistics for the specific views that will be stored and have a high resolution of storage. Selectivity for these views is evident in 1-year-olds, and it gets stronger till you end up with the highly selective views of adults. Okay? The dynamics and properties and selectivity of these manually generated object views early in life, this is the input that the neural systems for visual object recognition on which they depend. Okay? And the baby is generating that information. Okay? To their own exploration and action in the world. Now, there's a literature, and I'm going to give you the reference for it in a minute, that will take you to a review of this, showing that these developmental changes in self-generated views and the strength of the bias for planar views and for rotation and depth is related to object name learning and vocabulary size in 1 to 2-year-olds. It's related to object recognition from non-metric three-dimensional shape properties. It's related to the child's ability to recognize objects from unfamiliar views, from the back end, let's say, and to recognize objects in clutter. And this is again driven by the child's own activity, which requires that he sit steadily, hold objects, not fall over, so he can generate multiple views. All right. So manual interaction with objects and generating biased dynamic views of objects is part of the developmental pathway, part of the chain of events that leads to a mature system of visual object recognition and object name learning. All right. So again, babies through their own activities discover and solve tasks and build a pathway of development. Now, coming to the last principle I just want to talk a little bit about here, babies are not doing this alone. So if we really wanted to think about the brain, body, environment, there's not just the baby's brain connected to its body and the body connected to the brain, and the baby's body connected to the environment and the environment connected to the baby's body, but in that environment are other brain, body, environment systems. So babies develop as a body among bodies, and I'm just going to give you one little example here of how mothers use their bodies to organize attention and learning, and in terms of how we can think about that in terms of the sensory motor nature of development and of the social scaffolding of learning. So the example is about how babies use space and their body to learn object names. And in the first experiment in which we did on this topic, we just asked parents to teach their child names for things. And the babies were 13 to 15-month-olds. So this had no head cameras, no sensors. It's an old school kind of study. And what we found, okay, was that what parents did, this is a timeline, time in seconds across the top. The black shows the parent holding one object. They were to teach two object names. The white line shows, the white bars show they were holding another object. And on the side, it's whether the object was on the right side, on the parent's right hand, on the left side of the table, on the parent's left hand, or in the child's hands. And what you can see here is parents consistently kept, this parent, consistently kept the object indicated by the white bar either in her right hand or on the right side of the table, and consistently kept the object indicated by the black bar, the binoculars, on her left table and left hand. And parents did this. They spatially segregated the object very regularly. And they tended to name the objects, those little hash marks in the thing, when it was on one side of the table or the other. In a series of experiments, we have shown that this spatially dividing where objects are when you introduce them to very young word learners supports their learning. And that if the objects are moving all around the place in the event, it's much harder for them to get the name bound to the object than if you consistently present one object in its name and the other object in the other name on one side or the other. A lot of people think about this in terms of the spatial structure of working memory. But it also has, and that's a good explanation, but it also, I think, brings us home back to our first principle about the brain-body environment and how much it matters. So the embodied view is that you really cannot think about intelligence, the development of intelligence, the solving of any task without thinking of this continuous coupling of the brain to the world through the body. The classic cognitivist view, however, is that you have a sensory system with its own properties, you have a motor system with its own properties, and in between you have something that looks like a computer, where everything, sensory system does its stuff, then feeds the data to the computational system does all the smart stuff, and then it tells the motor system what to do. In the one robotics study that I'm going to tell you about that I was involved in, Toni Morse and the Cangelosi group looked at our results on how space was organizing the learning of these very young word learners, that they could learn if they had repeated examples of an object in its name in one location and repeated examples of an object name in its other location. And they asked themselves, what's the nature of the computational system? What's the nature of an autonomous system that could manage to do this? And Toni Morse's idea, was that perhaps what was happening, the reason why where the object was mattered, was because children, these young learners, linked the site of the object with its name through their own body's disposition in space, so that when they turned this direction, they thought of the binoculars, let's say, and that reminded them of having seen it before and the name heard. When they looked this way, they remembered the little springy item, and that reminded them of the name that they had seen before. It's working memory, reminded them of the name that they heard looking in that direction, and what the object looked like when they were looking in that direction. And in order to respond, okay, that's how you get the information in, but in order to respond, if somebody says, where's the spring, you've got to now get your body and your eyes and your hands to that object. So on the response side, you've got to have it out. So instead of having a separate system of sensory, computation, and motor, what they developed in the little iCub robot was an integrated system in which the visual field and the word field, the two things that need to be bound to learn an object name, were linked together through the momentary posture of the baby. Okay? They made a beautiful robotic model that explained all of our results, but it also made a really interesting prediction that they tested in the robot. If their account was right, that it was the body's disposition in space, then if I were to teach you an object name while you're sitting and then make you stand up, right, you might not be able to connect those if it's really being linked through your body's disposition in space. They showed that was true in the robot, and then in this paper, which is cited here, the PLOS paper, we went and tested that novel, never thought of before prediction in babies, and it is true of 18-month-olds. They need to sit still when they're learning, and if they move around, it changes the spatial indices, and they don't seem to link up multiple experiences to each other. Okay? So this is sort of interesting from my point of view as a developmental psychologist. What developmental robotics about is mostly taking what we know about babies and stealing it to tell us something about robots and how to build them. But this is a case in which building a robot based on what we knew about babies has actually given back a little new insights into how the spatial and working memory systems of young learners may be intimately tied to the spatial disposition of the body in space, its momentary disposition in space. Okay, so that brings us to the end. And I want to thank you for listening to this talk. Throughout the talk, I have littered it with citations that I think would be interesting to you. And I thank the Open Developmental Robotics course for inviting me to contribute a lecture. Good day.